So in this class we shall discuss some problems related to wave mechanical concepts in quantum mechanics, and of course these problems are related with de Broglie wavelength, uncertainty principles, and one-dimensional quantum L problem, infinite and finite quantum L problems. So the problem 1 goes like this: calculate the de Broglie wavelength of an electron having the kinetic energy 1000 electron volt. We know that the expression for the kinetic energy classically is given by kinetic energy equals P squared by 2m, so which is given as 1000 electron volt. We will convert it into joules multiplying with 1.6 in 10 power minus 19. So we will get P squared, which is equal to cross multiplying with 2m, that will give you P squared, which is equal to 2m multiplied by 1000 multiplied by 1.6 in 10 power minus 19. So your P squared, inserting the value of mass of the electron as 9.1 in 10 power minus 31 kgs, we will have this value. So which is nothing but your P squared will get as 2.912 into 10 power minus 46. And of course taking the square root, that will give us P, the value for P will be, momentum will be 1.706 in 10 power minus 23 kg meter per seconds. And we would like to calculate only lambda. So what is asked? Calculate the de Broglie wavelength of an electron is asked. So lambda equals h by P, which is equal to, the value for h will be 6.626 in 10 power minus 34 divided by the momentum value which we have obtained as 1.706 in 10 power minus 23. So we will get 0.39 in 10 power minus 10 meters. So lambda is nothing but 0.39 angstrom. So that is the first problem. Problem 2 goes like this: calculate the de Broglie wavelength of an electron which has been accelerated through a potential difference 200 electron volt. And of course through this potential difference only the electron will get kinetic energy. So the kinetic energy is given actually. So given that the energy gained by the electron is 200 volt, so of course classically the expression for kinetic energy equals P squared by 2m, so which is given as 200 electron volt. So we have just converted into joules, that will give us 1.6 10 power minus 19, so that will give us 3.2 10 power minus 17 joules. So kinetic energy, we have obtained the value for kinetic energy is given as 3.2 10 power minus 17 joules. And of course we can calculate P square by multiplying with 2m. So m is the mass of the electron, so 2 multiplied by 9.1 10 power minus 31 multiplied by the value that we obtained for kinetic energy, you just insert it, so which is nothing but 3.2 10 power minus 17. So we will get as 58.24 into 10 power minus 48. This is for P square. Taking the square root on both sides, we will get the value for P, the momentum, which we have obtained as 7.632 into 10 power minus 24 kg meter per second. So same problem as that of we have seen earlier, and momentum we have calculated, so we can get the de Broglie wavelength, which is given as h by P. So lambda equal to h by P, and of course h is the Planck constant. The value of Planck constant is given as 6.626 10 power minus 34 divided by, we have obtained the value for P 7.632 in 10 power minus 24. We will get lambda as 0.868 angstrom. So we will go for the problem 3. Determine the ratio of the de Broglie wavelength of an electron and proton, provided their kinetic energies are equal. So given that the kinetic energies of electron and proton are equal, and we are going to determine the ratio of the de Broglie wavelength, that is lambda E by lambda P. So we are going to determine lambda E by lambda P. So classical expression for kinetic energy is given as kinetic energy equal to P squared by 2m, and of course the expression for de Broglie wavelength is given as lambda equal to h by P. We just insert lambda equals insert the value expression for P from the above expression. So lambda equals h by P, instead of P just substitute this. So we will have kinetic energy multiplied by 2m. So lambda becomes h divided by root of kinetic energy multiplied by 2m. And the problem goes like this: the de Broglie wavelength of the electron. So we can keep it this as lambda E. So which is equal to h divided by root of kinetic energy E plus 2me. Similarly, for a proton, de Broglie wavelength of the proton, that will be lambda P equals h divided by root of kinetic energy proton multiplied by 2mp. We just divide these two. That we are going to calculate the ratio of the de Broglie wavelength of electron and proton, which is given as lambda E divided by lambda P, which is equal to h divided by root of kinetic energy of the electron multiplied by 2me divided by h divided by root of kinetic energy of the proton multiplied by 2mp. The problem, according to the problem, it is given that kinetic energy of the electron is equal to kinetic energy of the proton. So these two terms will get cancelled. Kinetic energy of the electron and kinetic energy of the proton will get cancelled, and of course 2 that also will get cancelled. H also will get cancelled. We will have lambda E divided by lambda P cross multiplying, that will give you root of mp divided by me. mp stands for mass of the proton and me stands for mass of the electron. And of course we know that mass of the proton is given as 1836 times mass of the electron. So we know already, we have already studied this one. So me will cancel. So root of 1836 will give us the value 42.85. So that is the ratio. Lambda E by lambda P, which is equal to 42.85. The question may be asked in this way also. Now the problem 4 exactly goes like this. Determine the ratio of the kinetic energy of the electron and the proton if the de Broglie wavelengths are equal. So earlier kinetic energies of electron and proton are equal. So now the kinetic energy, we have to find out the ratio of the kinetic energies of electron and proton. But the given that de Broglie wavelengths are equal. So lambda E equals lambda P. You just take, we have calculated already this one. So lambda E divided by lambda P, which becomes 1. So both are equal now. So use the same expression and we will have kinetic energy E divided by kinetic energy P. So E stands for electron and P stands for proton, which is equal to, use the same formula, we will get mp divided by me. And of course mp is given as 1836 multiplied by me divided by me. So me will cancel, we will have 1836. So this is the ratio of the kinetic energies of the electron and the proton. Now we will solve problem 5. If the electron has a speed 1000 meter per second with an accuracy of 0.004%, find the certainty of the location or the position of the electron. So we are going to find out the location where the electron is. We are going to find out. We are going to use only uncertainty principle here. So it is given that the velocity of the electron as 1000 meter per second, and of course with an accuracy it has been given. So this is given as the speed del V by V is given. So multiply and divide by m, that will give you del P by P, which is equal to 0.004%. I repeat, see, it's given as with an accuracy of 0.004%. So it's given as del V, okay, with an accuracy. So del V by V equals 0.004%. So multiply and divide by m, that will give you del P by P, which is equal to 0.004%. So del P by P will give us 0.004 divided by 100, which is nothing but 4 into 10 power minus 5. And of course we know that the momentum equals the product of mass and velocity. So mass of the electron, so the problem goes with the electron, so we'll have to use the mass of the electron. So 9.1 in 10 power minus 31 multiplied by, your velocity is given in the problem as 1000 meter per second. So we will get 9.1 in 10 power minus 28 kg meter per second. So P is given as this one. So what of del P? Use this formula. Del P by P equals 4 into 10 power minus 5. So del P, which is equal to P multiplied by 4 into 10 power minus 5. So P is given as 9.1 10 power minus 28, of course, multiplied by your 4 into 10 power minus 5, multiply these two will give us 36.4 into 10 power minus 33. So use the uncertainty principle, del x del P, which is equal to h, minimum uncertainty principle, which is given as del x equals h divided by del P. So we will get 6.626 10 power minus 34 divided by del P already we have calculated as 36.4 in 10 power minus 33. So which is given as 0.01882 meters. So it clearly says that below which we cannot measure. So this is the location where the electron can be measured, and below which electron cannot be measured with an accuracy. So it implies that the position of the electron cannot be measured to accuracy less than 0.0182 meters. So now we'll try to solve problem 6. This is also related with uncertainty problem, uncertainty relation, but we have used energy and time uncertainty relation. So earlier we used del x and del p, which is greater than or equal to h bar by 2, but here we have used del E, del T greater than or equal to h bar by 2. So let us see. The lifetime of an excited state of an atom is about 10 to the power minus 8 seconds. So we are going to calculate the minimum uncertainty in the determination of energy, that is del E we are going to calculate of the excited state. So we know the uncertainty relation is given as del E del T greater than or equal to h bar by 2. So use this relation and we can get the value for del E, which is greater than or equal to h bar divided by 2 del T. So it's given as h bar, we can calculate h bar equal to h divided by 2 pi, which is a reduced Planck constant, which is given as 6.626 10 power minus 34 divided by 2 pi. So the value is 1.054 in 10 power minus 34 Js. So divided by 2 multiplied by your del T. So del T is given in the problem as 10 power minus 8. So 2 multiplied by 10 power minus 8 we will have to divide, and we will get as 0.527 into 10 power minus 36 joules. But in addition to that, we can calculate the width of the spectral line when the atom de-excites to the ground state. From the excited state to the ground state, we can also get the value of width of the spectral line, which is given by, we know the Planck's idea, which is given as E equals h nu. So from this relation, del E equals h del nu. So del nu equals del E divided by h. So we will get, we have already calculated the value for del E, and divided by h will give you 8 in 10 power 6 hertz. So this is the limit to the accuracy with which the frequency of the radiation emitted by an atom can be determined. Now we will try to solve problem 7. This is related with quantum well problems, and of course we are going to normalize the wave function. So wave function is given as psi of x. It's a one dimension one, so psi of x equals a e power minus alpha x squared. And of course the moment when we look into this expression, we can find out that this wave function is related to Gaussian wave function, harmonic, linear harmonic oscillator. Often we'll be using this one because e power minus alpha x squared is there. So it is exactly symmetric on either side. So where capital A and small a are constants over the domain, where x lies between minus infinity and plus infinity. So now we are going to get the normalization constant. Of course, we are going to get the value for capital A. We know the normalization constant is given as capital A square minus into plus infinity integration psi star psi dx, we know already, which is equal to 1. Psi is given as a e power minus alpha x squared. So psi star also will be the same expression as e power minus alpha x squared. So multiplying these two will give us e power minus 2 alpha x squared dx integration, which is equal to 1. We are going to get the value for this integrand. So using the standard integrals, we know the value will be minus infinity to plus infinity integration. The integrand is e power minus 2 alpha x squared dx will give us root of pi by 2 alpha. So just substitute instead of this, just substitute this value, we will get a squared root of pi divided by root a, which is equal to 1. So a squared is given as root of 2a divided by pi, and a is of course 2a divided by pi to the power 1 by 4. Now we have obtained the value of capital A. You substitute in this expression in the wave function. So psi of x equals 2a divided by pi to the power 1 by 4 e power minus alpha x squared. So this is a complete expression with a normalization constant. So thus we have normalized the wave function. Now we will discuss problem number 8. Calculate the permitted energy levels of an electron in a box 1 angstrom wide. So this is a one dimension box with the width is given as 1 angstrom, so 10 power minus 10 meters, and we are going to get the permitted energy levels. We are going to get the expressions for E1, E2, E3 and goes on. And we know that we have already studied in a quantum problem, we know already that the expression for energy levels is given by En equals n squared pi squared h bar squared divided by 2ml squared, we know already. So substitute for pi squared, which is 3.14 squared, multiplied by h bar squared, we have already got the expression which is like reduced Planck constant. The value is 1.054 in 10 power minus 34 divided by 2m. M is the mass of the electron, so 9.1 10 power minus 31 kgs, multiplied by L is 1 angstrom. The width is 1 angstrom, so 10 power minus 10 whole square. Just take the power out first. So we have n squared 3.14 squared multiplied by 1.054 squared multiplied by, you are going to take the power, total power outside. So this is 10 power minus 68. You bring the powers from denominator to the numerator, that will give us 10 to the power 31 multiplied by 10 power 20. So solving all the power, that will give us 10 power minus 17. The remaining thing that we can get, the value will be 0.6018 multiplied by 10 power minus 17 joules. Now dividing by 1.6 10 power minus 19, that will give us the energy value in terms of electron volt. So we will have 37.61 n squared electron volt. Suppose we want to calculate for the first energy level for n equal to 1. So we have E1 which is equal to 38 electron volt, and E2 will be 38 multiplied by 2 squared, that is 4, which will get us 152 electron volt, and E3 will give us 38 multiplied by 9, so which is nothing but 342 electron volt, 342 electron volt. So like that we can calculate a lot of permitted energy values as e to the power infinity even. Okay. So now we will go for problem number 9. Find the expectation value of the position of the particle trapped in one dimension box. So we are going to find out the expectation value of the position of the particle in one dimension box. Let us see, and we are also going to get the expression value of momentum also. So let us see how it goes. So we know that the normalized wave function of the particle is given by psi n, which is equal to root of 2 by L. Already we have normalized, okay, root of 2 by L sin n pi x by L. The expectation value is given as x sandwiched between your ordinary normal wave function and its complex conjugate. We have already discussed earlier in the expression of expectation value earlier. So this is given as exactly this expression. So now we will substitute for psi star and psi. Of course both are equal, there is no I part, so we will get the expression value of x will be root 2 by L multiplied by root 2 by L, that will give us 2 by L, and x I have pulled out here, so that will be the remaining part will be sin squared n pi x by L dx, and we are going to use sin squared x equal to 1 minus cos 2x by 2, and this 2 and this 2, that is 2 in the denominator and 2 in the numerator will cancel, and you substitute, then we will get this expression. So we will have 1 by L integration 0 to L x multiplied by 1 minus cos 2 n pi x by L dx. So now we will separate these two parts. This is the first part and this will be your second part. So first term and second term. So we will try to solve second term first, we will get the answer. Then after that we can insert the values for the first term. It will be very easier. So now we will go for the difficult part, which is the second part. So second term. Second term we have taken as x, we are going to solve the integration 0 to L x cos 2 n pi x by L dx, and we are going to use udv method. So integration udv equals uv minus v du. We will take the second term and we are going to consider x as u and du, so dv as cos 2 n pi x by L dx. I repeat, we are going to consider x as u and this term, that is cos 2 n pi x by L dx as dv. So u equals x means we will get du equals dx. dv equals cos 2 n pi x by L dx means just integrate on both sides, we will get the value for v, expression for v, which is equal to sin 2 n pi x by L divided by, so integrating, that will give us 2n pi by L. So use the formula, integration u dv equals uv minus v du. So that will give us now uv. What is u? U is given as x. What is v? V is given as this term, sin 2n pi x by L divided by 2n pi by L. You substitute here uv minus v du. V is given as this expression, du is given as dx. So this expression. When you are going to substitute the limits, first we will substitute the limit, upper limit. So instead of x, you are going to substitute L, and this L will cancel. And of course we know sin 2n pi, sin 2 pi, sin pi, everything will become 0. So this term will become 0 when you are going to substitute the upper limit. What is the lower limit? When you are going to substitute the lower limit, sin 0 is 0. So this term will become 0. Now we will go for this term. So again the second term becomes, this is our second term, 1 by L, integration 0 to L, x cos 2n pi x by L dx, which is equal to, and of course this minus sign, exactly we have written as minus 1 by L, L divided by, that is in the denominator we have 2n pi by L. Just to bring this term to the numerator, that will give us L divided by 2n pi. So 0 to L, sin 2n pi x by L dx. And this cell and this cell will get cancelled. So we will have 1 divided by 2n pi, and we are going to integrate. So sin 2n pi x by L, upon integration we will get minus cos 2n pi x by L divided by 2n pi by L. So bring that term to the numerator, that will give us L divided by 2n pi. So after the integration we are going to substitute the limits, and of course when you are going to substitute the upper limit, so 2n pi x by L, just substitute instead of x, substitute L, L will cancel, you have cos 2n pi. Cos 2n pi becomes 1, we know already. And of course when you are going to substitute the lower limit, that will give us cos 0, again 1. So 1 minus 1 will give us 0. So your second term becomes 0. And what about the first term? First term is 1 by L, integration x dx, that will give us x squared by 2. Substitute the limits, that will give us 1 by L multiplied by L squared by 2. The expectation value will be L by 2. It means that particle, the position of the particle is exactly at the center of the box. Okay, so that is asked. So find the expectation value of the position was asked in a one-dimensional box. It exactly lies at the center of the box. Now we will go for problem number 10. Calculate the expectation value of the momentum. So in the earlier problem we calculated the expectation value of the particle, position of the particle, so which lies exactly at the center of the one-dimensional box. Now we are going to get the expression value of the momentum of a particle trapped in one-dimensional box. A similar way that we are going to apply. So we know that the normalized wave function of the particle is given by psi n equals root of 2 by L sin n pi x by L. We know already. The expectation value of the momentum is given as the p is sandwiched between psi and psi star, normalized ordinary wave function and its complex conjugate. And of course we know px equal to minus ih cross del. You just substitute instead of p minus ih cross d by dx, the operator form. So now we are going to substitute psi n, and of course psi n star also will be the same as psi n. So root of 2 by L sin n pi x by L. So substituting, that will give us exactly this expression. Now just to differentiate with respect to x. So this wave function is differentiated with respect to x. So we will get cos 2n pi x by L divided by n pi by L. So bring that term to the numerator, that will give you have n pi by L. Okay. So we will have minus ih cross 2 by L n pi by L. We have sin 2 n pi x by L cos n pi x by L dx. And of course we can bring these 2 inside, that will give us 2 sin x cos x. Okay, 2 sin x cos x is equal to sin 2x. And I think here there is a mistake here. We have cos 2 n pi x by L divided by n pi by L. So we will get L divided by n pi. Here there is a mistake. We just correct it. So this must be L divided by n pi, and of course L will cancel. And 2 we are going to bring this term here. So that's a mistake here. This L will cancel. We have minus IH cross divided by n pi. Okay. So sin 2 n pi x by L dx. So after the integration will get minus cos 2 n pi x by L divided by 2 n pi by L with integration value 0 to L. So that will give us now. So here it is correct. L divided by 2 n pi. So now it's correct. L divided by 2 n pi cos 2 n pi x by L. I have interchanged with the minus sign. See, I have removed the minus sign and I have changed the limits. So it becomes L to 0. Instead of 0 to L, I have removed the minus sign. So it becomes L to 0. Now you substitute the upper limit. Upper limit is nothing but 0. So we have cos 2 n pi 0 divided by L. Cos 0 is 1. Just substitute the lower limit. So which is nothing but, instead of x you are going to substitute L. L will cancel. So you have cos 2 n pi, again this becomes 1. So 1 minus 1 is 0. So the expression value of the momentum of the particle is 0. So earlier we discussed that the expression value of the particle is exactly at the center of the box. But here the expression value of the momentum of the particle is 0. So it clearly says that it obeys uncertainty principle, uncertainty relation. That is, the moment at the center of the box, the particle exactly lies at the center of the box, and we know the position, whereas the momentum cannot be known because momentum is 0. So it supports the uncertainty relation. So now we'll go for the last problem. No, last but one. Verify the orthogonal property of the wave functions of the particle in one-dimensional box. And of course we know the canonical delta function. So when for the two indices, either j or I or j, or either n or m, if they are equal, the answer will be 1. If they are not equal, answer will be 0. So we know already this is a canonical delta function. So now we are going to verify the orthogonal property of the wave functions of the particle in one-dimensional box. And of course we know the wave function is given as root of 2 by L sin n pi x by L, we know already. And we are going to verify psi n star psi m dx equal to 0 for n is not equal to m. So we will just go with the complex conjugate of this function and integrate. So we have 1 by L integration 0 to L 2 sin n pi x by L sin m pi x by L dx. So just we have used the formula 2 sin n pi x by L sin m pi x by L. We have used the formula as cos n minus m pi x by L minus cos n plus m. And of course we know the formula 2 sin a cos 2 sin a sin b will give us cos a minus b minus cos a plus b. So use the formula. We will have this expression. Now we integrate individually. That will give us sin n minus m multiplied by pi x by L divided by n minus m pi by L. Similarly the other term. We just substitute the limits. And of course we are now going to substitute the upper limit. The L will cancel. So sin pi is 0. So this term also will become 0 and this term also will become 0. So the final answer is 0. So it has been verified as the orthogonal property. That is integration of sin psi n star psi m dx equal to 0. Hence we have verified the orthogonal property of the wave function of a particle in one dimension. The last problem is deduce the probability current density. So we are going to get the expression for current density of the wave function. The wave function is given as psi equals a by r e power I k r, and of course we know the expression for any plane wave is given as e power I k r, a e power I k r, and here it is given as e power I k r by r. So it is a spherical wave. So expression for the spherical wave is given as a is normalization constant. So your psi will be a divided by r e power I k r. So e power I k r by r is a spherical wave, expression for the spherical wave. Here A is the constant, the normalization constant of course, and K is a wave vector. So we know the expression for probability current density is given as J. Current density is denoted as J, which is equal to IH cross divided by 2m psi del psi star minus psi star del psi. In the problem it is given as a psi equals A divided by R e power ikr. So just to calculate the complex conjugate of this function, which is nothing but psi star, which is equal to A divided by R e power minus ikr. You just differentiate with respect to R, that will give us del psi. So here A by R is there, here e power ikr, two R's are here. So we will have to keep one R as constant, we will have to differentiate the other one, plus we will have to differentiate this keeping the other R as constant. So when you are going to differentiate with respect to R, will give us, for example, we just keep the R as constant, so that will give us A by R. Differentiate this, that will give us ik e power ikr. Now you are going to keep e power ikr as constant, you are going to differentiate A by R, that will give us minus A by R square. So like this. And taking the complex conjugate will give us this expression, del psi star equal to, just instead of I, just go with minus I, that's all. So minus aik by R e power minus ikr minus A by R square e power ikr. So your current density expression is given as this. We are going to substitute all the expressions here in the expression of J. So that will give us, instead of psi, we are going to substitute A by R e power ikr. Del psi star already we have calculated the expressions for del psi star. This is your del psi stars, and this will be your psi star, and this will be the expression for del psi. So now pull A out. So here A is common, so just pull out. Already one A is here, so A squared. Here also you pull A out, already one A is constant, you pull, so that will give us A squared. You pull A squared out, that will give us A squared. So first, so IH cross divided by 2m mod A squared we have already taken out. The remaining term will be e power ikr by R in the first expression, and here we have ik by R e power minus ikr, and of course here you have minus e power ikr by R square. And in the second term we have e power I minus ikr by R, and the rest of them we have written exactly like this. So multiply now e power ikr by R inside, so that will give us e power ikr multiplied by e power minus ikr, that will give us 1. So remaining term will be minus ik divided by R multiplied by R will give us R squared. And the next term will be again e power multiplied by ikr multiplied by e power minus ikr, and R multiplied by R squared will give us R cube. So we have minus 1 by R cube. And this term exactly similar to this one, so we will have minus ik divided by R squared, and this term will become minus minus plus, so that will give us plus 1 by R cube. So this term and this term will cancel, that is the second term and fourth term will cancel. Remaining terms can be added, you will get minus 2 ik by R square. So we will get I into I squared minus 1, already one minus is there, so we will have plus. So plus your h bar is here, k I have brought it inside, so here front, so you have h bar k divided by m r squared, these two and these two will cancel, you have h bar k divided by m r squared mod A squared. So which is the expression for current density. So this is the expression for probability current density of the wave function. So that's all. We will see in the next class. We have solved some problems related to wave mechanics and concepts in quantum mechanics. So thank you, students.